Hi, Doug. I think you're still muted.
Forgot Zoom has another mute. I usually just use my phone for muting, so I use too many different platforms. Okay, can you see my my presentation screen right now?
Yep, I can see it. I've got it up on the screen for the students. You can kind of see it behind me there.
Perfect.
We're just for everyone to come from their previous class over to this one. Looks like everything is working great. I'm going to run and get a drink real quick while I'm waiting for the students, and then I'll be right back.
Okay, I'll probably do the same.
Okay.
I decided I'm going to mess up the seating arrangement that we've all created. Like, do I dare? Here we go.
Probably be easier for the question to ask. To be closer. Hello, Brooke.
Hello. Brooke, do you, find another place to sit somewhere? Or-
Oh,
Eight
so
o'clock
I've actually
class.
been, so my boyfriend doesn't have any classes in the morning, and so, so I can get up a little bit later, and I don't have to get ready, I'll like, just do the class at home, and then right after, Ed will drive me, or like towards the end of it, we'll like get the plan job and stuff, so. Did you end up looking at the classrooms that they had open?
I didn't, I found out they're over there,
Yeah, they're in Roya, I think,
so
too.
I was gonna say, 'cause I'm sure more people are gonna come in the lobby and stuff.
Yeah.
Skill-wise, so.
Hey Porter, hey Kingston, hey Darren. You guys hear
How's it
okay?
Yes.
Awesome.
Yeah.
Great. I'm missing just a couple people, Doug, so we'll wait just another minute.
Sounds good.
Hey Trevor. Can you hear okay, Trevor?
Yeah, I can hear you.
Awesome. Okay. Well, we'll go ahead and get started, even though a couple people might still show up. So everybody, this is Doug Bowman from Nucl. He is going to tell us all about Nucl and the reactor that they're designing. This is the first year class, Doug, and we have just started to talk a little bit about PWRs and BWRs and kind of the basics of what they are. And so you kind of get to be the first contrasting new design, just kind of talk about your reactor. So I will turn it over to
Excellent. Okay. Good morning, everybody. My name is Doug Bowman, as Mackenzie said. My job is the plant operations supervisor at Nucl Power. I am going to provide you guys with an overview of the design today. You'll find out it actually fits neatly into one of the categories you've already learned about when we talk about it. This is just intended to be a bit of an overview. I only got about 30 slides or so. This is kind of out of one of our marketing decks, slide decks, but it should be able to get into enough detail, and hopefully my real hope is that you guys ask me questions more than me sitting here presenting to you from these slides. A little bit about me, you guys can ask me lots of questions. I spent 24 years in commercial industry. I was SRO licensed at both Byron and DC Cook in the Midwest. I did all kinds of different jobs from, plant engineer up through training, work control. I was an operator for a long time and filled most all the supervisory roles at one point or another in the operations side. I've been in Nucl for 6 years now, really working in figuring out how we're going to operate the plant design that we've put forth. So hopefully you guys will walk out of here with a lot more information than you had before about Nucl. If my slides want to work, there we go. Okay, our usual disclaimer about the DOE supporting our work. So NuScale Power, who are we? We started in 2007, a long time ago now, out of some work that was done at Oregon State University in their nuclear engineering department. That initial concept was called the MASLAR. It was initially supported all the way back in 2000. Work went on for a few years. They had a fairly small staff up until 2011 when Fluor, who was a large construction engineering corporation, came in and provided funding in 2011. From there, things really pretty much took off for NuScale. In 2013, we won a competitive DOE funding opportunity. That's when I came in, about 2014, I came to NuScale. We got lots of patents, we got lots of employees, et cetera. Currently, we are the only SMR, small modular reactor design, to receive a design approval from the US NRC. So you can see on the pictures over on the right side, this is our test facility. Let me see if I can get the laser pointer to work here. On this. Perfect. We've got our NIST facility, which is at Oregon State University still. It's a thermal model of the plant that we use to confirm our safety design codes. And then we've got a picture of the simulator, the thing that you guys should be most interested in. We'll get into a little bit more about that. Obviously, I've spent a lot of time in here and helped out with designing the screens and some of the work we've done there. So, all right. So what is NuScale, the power module? So, we fit into this category called small modular reactor, but that's not really a description of the technology. It's kind of more a description of it's less than 300 megawatts and it's modular, so it's capable of being fabricated off-site and assembled on-site. So that really doesn't describe the technology. The real technology is we're still a pressurized water reactor. So we use light water as a moderator. We still use boron as a fission poison, which is pretty much in line with what traditional pressurized water reactors use. The real difference is we're small, only about 60 megawatts electric compared to a large traditional PWR. The two I was licensed at, they were in excess of 1,000 megawatts of electrical output, and their thermal output was over 3,000 megawatts. And we're integral, meaning that there's no large piping, we don't have separate steam generators, it's all in one vessel. So we'll talk about that a little more. Right now, our current plans are to each module produce about 60 megawatts electric, and we have them bundled into a group we call a 12-pack, oddly enough, where we can put out 720 megawatts gross. That's the design that was approved by the US NRC. We certainly are willing to design anything. The Canadians have a little bit of interest in this right now. They're actually asking us to look at building a 6-pack instead of a 12-pack. So we're examining those kind of changes to the design as well. All right, here's your typical pressurized water reactor. You've got a core, you've got a pressurizer that maintains pressure. You have a number of steam generators depending on your design, and you got some reactor coolant pumps. Well, we moved all that stuff, meaning the pressurizer and steam generators, inside of the reactor vessel, essentially. And we got rid of the reactor coolant pumps, is really what NuScale did. So we're a natural circulation reactor as well. Makes it a lot simpler. It does have some downsides in terms of the amount of power you can put out because of the flow rate, but it is a lot simpler, and trust me, reactor coolant pumps can be quite a problem from a maintenance and an operations standpoint. So here's what it looks like when we get down to it. You've got and we actually did it one step further and included containment in this package, right? So we've got a containment vessel outside. We've got a reactor coolant pressure boundary inside. Your pressurizer sits at the top behind a baffle plate. The steam generators are up high. They're a very interesting design called the helical coil steam generator. Very different than anything you've traditionally seen. And then our core sits all the way at the bottom where it can stay covered with water all the time. So that's what it looks like in pictorial cutaway view. The size of it, it's about 76 feet tall, 15 feet in diameter. We, of course, claim it to be truck transportable. I would say it's at the very limits of being truck transportable. It's very large, very heavy still, despite all that work. Again, you have an average American standing next to it, so you can see how big it really is. It's quite large. But in comparison to a large pressurized water reactor, you can see that it's relatively small. All right, this is about the best diagram I can show up for you that shows overall how the plant works. So we've got a schematic diagram of the plant here. I'll walk through it. The reactor core sits at the bottom. Above it is what we term a chimney. So your water, as it's heated, will flow up through this chimney till it gets to the top of the chimney, and then it will drop down the outside in what we term the downcomer through the steam generators. So this comes out at the coldest, once it's out of the steam generators, it's at the coldest spot it can be. Call that T-cold. And then it re-enters the core at the bottom of the chimney and flows back up. And that's your natural circulation flow path. Steam comes, so on the secondary side, we've got a secondary system with condensate pumps and feed water pumps and some heaters for efficiency. The feed water pumps will drive water into the steam generators at the bottom in what we call feed water plenums. That water rises up through the steam generator and boils as it goes through. It becomes superheated at the top, and then we come out as main steam back and feed the turbine to generate electricity. Again, we have a pressurizer at the top. We do have control rod drives. These are actually also fairly traditional control rod drives. They're what I'm used to from Westinghouse. I call it magnetic jack design. We have pressure relief valves at the top and reactor vent, the part of our emergency core cooling system, the reactor vent valves and the recirculation valves. Outside, you see this blue area is actually the pool. So the real genius of the design in terms of safety was the fact that we took the struggles you run into when you get into problems at a power plant. You know, a lot of them are based on a lost coolant accident or other accidents that are discussed. But really, one of the major problems that the industry runs into is trying to connect the core to the ultimate heat sink. So the genius of our design is we took the containment and the reactor coolant system and we dropped it into the ultimate heat sink. And we make it very easy to connect the core and get that heat out of the core, to get heat out of the core and into the ultimate heat sink. So it's very closely coupled. You can see the water out here is actually the pool that we talk about. And I'll show a picture, cutaway picture of the building later. And you have this containment volume here. This containment volume is maintained at a high vacuum, and we use that for insulation, much like your thermos would work for coffee. And then inside here is the reactor coolant system, which is maintained at a relatively high temperature. Our average temperature is 545 degrees at power. And each turbine, so right now with the way our design's built, each module, each of the 12 modules has its own turbine generator and its own feed water system. So you eliminate you could take a single unit offline and you still have 11 units operating. So from an electrical generation standpoint, it's really advantageous in comparison to a large plant where when you take it offline, you're losing 1,000 megawatts. Here, we're only losing 8% of our total output when we take a unit offline. Any questions so far? All righty, we'll keep moving. Okay, so this is the cutaway view of the reactor building. So this is the building that houses all of the modules. You can see we have modules, half of our 12-pack is aligned on this side of the building. There are 5 shown here right now, and the 6th one is actually out for a refueling outage. Or we're putting it in. We can take our pick there, but we'll call it a refueling outage. This blue area is the reactor pool. In our current DCA design, this pool is 7.5 million gallons of water, so a very, very large volume of water. We are very unusual in the way we refuel, rather unique. Rather than refueling in place, we actually use the reactor building crane to pick up the module, and we disassemble it using this containment vessel flange tool and the reactor flange tool. And when you come out of the reactor vessel flange tool, you take just the upper portion of the module and you move it to the dry dock, which is in the back behind the refueling machine here. And I do have another overhead view that'll show that better And what's left behind is the reactor vessel, which is the lower part of the reactor vessel, and it contains the core. So your fuel assemblies are in here, and then we refuel using a refueling machine. This is actually a fairly traditional refueling machine design. It's just got a longer arm on it to pick up the fuel. It takes the fuel out of the reactor vessel and places it in the spent fuel pool, and then we move that back and forth to do refueling. And then we reverse the process. We pick up the upper module, we reconnect it to the reactor vessel, and we reconnect it to the containment vessel flange, and we place it back in its operating bay. So here's an overhead view of the reactor building. Again, this shows all 12 modules. Part of them are obscured by the reactor building crane shown, but we've got modules aligned here along the sides of the reactor pool, this central area where you can move the module down. Here's the location of the containment vessel flange tool, the reactor vessel flange tool, a refueling machine and spent fuel pool. And then you can see in the back here, we have the module import trolley, and this is an area we call the dry dock. And most of your outage work would actually happen back here. The upper module contains most of the active components for the module that need to be maintained. So all of your instrumentation, all of your valves are essentially moved with the upper module. And this is an area that has a door that can be closed off, and we can drain it down to do maintenance work on the upper module.
I have a question, Doug. So this,
Sure.
this pool with multiple modules in it, when you foresee someone building this, would you encourage people to already build this large enough to hold your 12 pack? Or could they build one that was for, say, 6 and then add another pool? What design are you going through with that pool?
So
Does that make sense?
Go ahead.
Oh, that was it.
Okay. So this design, what I'm showing you is what we submitted and was approved by the NRC. It's a 12 pack. As I said earlier, the Canadians, for example, are interested in smaller outputs, so they're asking us to consider designing a 6-pack. It's a question of somebody being interested in paying for the design work. There's a lot of design work that went into this reactor building. It's seismic category 1, so it's resistant to all the largest earthquake expected at the site. It's very expensive to build the building. One of the largest costs surrounding building a new scale plant. So redesigning it would also be very expensive, but there would be some advantages in sizing, et cetera. So that's why we're certainly always interested in working with anybody who wants to buy one to try to design them the best fit solution for what they need. So yes, to answer your question, yes, we would certainly potentially redesign, but our approved design right now is the 12-pack.
And does it change your design at all? They build this and they only want to put 1 unit in to start. You still build the pool for the 12?
So are you start your question off again? Sorry.
So the pool holds the 12 modules, right?
Yes.
So some application only wanted 1 module to start, and they were going to wait and add more as they needed more or had funding to keep building. Would you still just build this 12 pool capacity, essentially?
I would say yes. This is certainly what we're looking at building on the IML site. Again, it depends on what you eventually want your final station output to be. We could certainly build the building and then put 1 module in and start operating it. It's one of the big advantages of the design with the 12 individual modules. You can start recouping some of your investment right away to pay for doing the work by getting a module in and getting it started, and then you can add more later as you need it. So we certainly see that as an option for people to use if they wanted to build a plant.
Thank you.
Mm-hmm.
So this could be like an investment, like somebody could purchase this and supply power to a city, or do you have to be like licensed and everything to be able to purchase?
Could you hear that, Doug?
I heard a question about licensing and being able to purchase.
So how you have to get licensed to be able to put this in? Can like a city Just
Yeah.
purchase this.
To fund it, could he fund it and have income from it?
So the question is, so like if Bill Gates wanted to fund it and have income coming in from this, could he just fund this?
Sure. I guess I'll take the example. I'm certainly used to in my past history dealing with large utilities. So this is my first time where I've had to deal with in UAMPS with a small group of municipalities. So UAMPS who's intending to build at INL is a group of municipalities. So they are UAMPS as an entity will hold the license for the facility, which the NRC needs an entity that holds that license. But however, you have all these small cities that have added money given money to UAMPS to explore and then eventually build this plant. So I guess in that example, UAMPS holds the license. However, a city like, I don't know, Falls could put money into it and say, well, we want part of that power. And, how much they invested would, certainly dictate how much of the power they got to use, I guess. Is that answering the question?
Yes. I don't know. Do you guys know what UAMPS is? Have you heard that before? A couple people have.
I get into it a little bit later in the presentation.
Okay.
All right, real quick site layout from an overhead view. So this is essentially the certified design right now and the layout of the site. Currently sits on about 34 acres. Not real big, but not real small either. It includes a lot of components inside of it. So in the center, we've been talking about the reactor building. You can see that's shown here. On each side of it, flanking it, are 2 turbine buildings. Each one of these contains the 6 turbine generators for 6 of the modules. We have a control building. This is actually where the control room sits. This is certainly an unusual design feature for a U.S. plant to have a control building outside of the reactor building, for example. But it's very well protected. The actual control room is actually below grade, as well as the modules are completely below grade. The pool is below grade. So they're well protected from anything that could happen. This building, the reactor building, is actually aircraft impact resistant, so it's capable of surviving a strike from an aircraft. We have a central utilities building, which contains a lot of air compressors, chillers, that kind of equipment. And then we have a rad waste building, which also serves as kind of a maintenance facility for the plant. It's really the way we get modules in and out of the reactor building. We have to bring them in through the rad waste building. And then we've got an annex building, which just contains offices and other workspaces. This is all surrounded by, this is your double security fence. Traditionally, for a nuclear power plant, you'd have a double security fence. So this is our secured area. Outside of it, we have the cooling towers. These are water-cooled cooling towers, or evaporative cooling towers. So these large Bravo and Alpha are for the circulating water in the main condenser. This is a service water tower that supplies cooling for other needs. We've got the switchyard. And then outside of the area, we'd have an administration building and a warehouse and parking, et cetera. So that's an overall look at the layout of the site that we anticipate. Now, the design that UAMPS, the company that's building at INL, has requested that we consider dry cooling for the main condenser and the service water. So that will change the design substantially. And we have to move large dry condensers inside of the fence, and they will take up a large area because when you go to air cooling, you get to very large sizes. These cooling towers would go away, and you'd see a different layout in terms of having the condensers and some cooling system for the service water as well. And air cooling is a unique technology. I don't have any experience with it. We're currently investigating and doing some design studies on that. Okay, so we'll talk a little bit about safety of the design. I talked a tiny bit about it, but we'll get into more of it. So the design's incredibly safe and very simple. It's really the hallmark of it. Honestly, this design could have been built decades ago. And to me, we really missed out on the opportunity with what I'm used to operating from my past life to what this is. It's incredibly simple. It's incredibly robust, and it just works very well. So we use natural convection. It's passively safe. We don't require any active components for safety to remove heat. Very seismically robust because we don't rely on any electrical components for the safety of the plant. You wind up with a very seismically robust design. It's very resistant to any kind of earthquake. Small and simple. The core is about a 20th the size of large reactor cores, and the integrated design means that we don't have to consider what's termed in the industry a large break, a loss of coolant accident, where the largest pipe in the system, you have to assume that it breaks for assessment of safety in a traditional PWR or BWR, for example. In this case, we don't have any pipes. We just have a vessel, and we can assume that vessel doesn't break. Defense in depth, multiple additional barriers to protect against the release of radiation in the environment. Again, we use conduction and convection, two forms of heat transfer to remove the energy, and we use the natural process of heat rising and cold water dropping, meaning gravity and buoyancy, to move the water around inside the primary loop. This also allows us to, we are currently pursuing the concept of a site boundary emergency planning zone. When you build a plant, you need to describe over what area surrounding the plant you're going to develop emergency plans for. Traditionally, plants have had to use a 10-mile EPZ radius. We have, based on our size and safety of the design, are currently proposing that our emergency planning zone be the site boundary. Realized emergency planning at a large PWR or BWR takes up a huge amount of time and resources. Us being able to shrink that emergency planning zone down to the site boundary would be an incredible savings to our eventual customer. Another key part of the design, does somebody have a question, I hope? Okay, another key part of the design, we intend to, what's termed in the industry right now, flexible power operations. We as a design, we have built the plant and the modules to be able to balance against renewables. So on a grid, when you have a grid, you have to constantly be matching the electrical output of all of the units that are providing power to the grid to the amount of electrical output you are outputting to your customers, right? So every time somebody turns on a light, that might be a bit of a overstatement, you need to make a change in your generation to support that. Now, in the past, that's been done with what would be termed dispatchable units. So you're able to control the output of, for example, a NuScale plant. We can control how much power we put out by changing certain parameters. When it comes to renewables, meaning primarily wind and solar, you're really reliant on the weather. Changes in wind can change your amount of generation. You know, the cloud comes over and it changes the amount of solar power that's being generated. So you need a dispatchable unit to be able to balance that power on the grid. And that's what we're really showing that the NuScale design can do. There are new requirements out there that the Electric Power Research Institute put out for these for this flexible power operation, and we can meet or exceed all of those requirements for our plant. And this is actually a graph out of a study we did against a wind farm called Horse Butte, and we looked at its output, and we looked at the overall grid demand for the day, and we showed that a NuScale unit could easily balance against those changes in output from the wind farm and match it to the electrical demand. At the top, you'll see that we've got this dotted line is actually the electrical demand curve. This blue line is the Horse Butte wind farm's output, and then we laid on top of this, the hypothetical NuScale plant being able to generate the power and change power rapidly enough to balance that load to meet the electrical demand on top of what the Horse Butte wind farm was putting out. Another discussion about renewables, NuScale and the 2020 California duck curve. Sounds a little odd, but what's what's winding up happening is that there's this short period of time in California as their solar goes off, and it actually they actually run into problems where what they call the duck curve. As you can see, it's shaped a bit like a duck. In the afternoon, when the solar starts going, afternoon evening when the solar starts going away, they have this huge need for additional output, and we basically laid our ramp capability on top of that to demonstrate that we could meet that demand if we needed to.
Is anybody in California interested in a NuScale? I know UAMPS is mostly, right?
So California currently has a moratorium against building new nuclear power plants, state moratorium. We would love to see them build one, and I would tell you that based on some of the things that have happened this summer, and that I believe will continue to happen in California, they desperately need additional generation. Beyond what they have, they've really put forth this idea that you can supply a grid with solar and wind, which really isn't true under current technologies. And even if you were to substantially expand battery capacity, batteries don't generate electricity, they just store it. So, you've got to now build more solar and wind farms to charge those batteries to meet those off-demand peaks. And if the battery runs out of electricity, you're out of electricity. So there's a lot of issues with the concept of a fully renewable grid where you're based solely on solar and wind right now, and batteries even. There would still run into some issues. For example, the state I live in right now. Go ahead.
So what is the site and the INL planning to do with the electricity that they produce, or the power or energy?
I think, hang on, I'm just flipping through my slides. I thought I had a slide in here that talked about that. I'll just go ahead and go back to where I was. I'll try to answer that question. So this plant that's being built on INL is intended to replace a couple of coal plants that UAMPS, the Utah Association of Municipal Power Systems, is retiring. They need additional generation. Their CEO has stated they recognize that new generation needs to be carbon free. So they are exploring the option of building a nuclear power plant to replace those coal plants that they are going to have to retire. So that's intended to go, most of that power is intended to go onto UAMPS's grid and supply their customers, which are primarily, small municipalities. Part of the output is intended to go to INL, and there's actually one module they call the jump module that's going to be used it's intended to be used for research, including some of these coal generation ideas that I have on the slide currently. So there is also a regulation out there, I think by 2028 or maybe later, I think it might be 2030, that all the national labs have to go carbon free as well. So that's part of the reason why I think we got our plant sited at INL to help with that process as well. Does that answer your question?
Yeah.
Yes, but I think there's another one.
Go ahead.
What's the cost comparison for energy from coal or oil to nuclear?
Did you hear that?
Well, yes. So those are three very different questions. And I'm going to probably not answer them exactly like you want me to, but I'll try to answer them. When you burn coal, and I'll use coal for an example, you're dominated by your fuel cost. Coal is what costs the most out of all the money you have to put out to generate electricity. When you look at nuclear power, the fuel cost is a small portion of what we do. Your real money is in operations and maintenance of the plant. And that means a great deal of your money is in how much you pay the people who work there. So you're really dominated by your personnel costs and what it costs to maintain the equipment rather than the fuel cost. So over the years, I mean, originally nuclear power plants, when they were first built back in the 60s, were intended to be operated by very small staffs. The plant I was at, Cook, originally had a staff of like 350 people. They have well over 1,000 people that work at that site now. And that's really due to, and they really haven't changed the number of people. For example, the number of mechanical maintenance people that work there really hasn't changed that much. It's all the admin burden and all that overhead admin burden from regulation that really drove the cost up of nuclear power. So I'm probably not answering your question exactly the way you wanted me to, but so we're working very hard in our design to, and I'm going to talk about that in a minute, to reduce the costs, especially, oddly enough, personnel costs, and hopefully regulation costs as well. We've got a lot of, beyond the unique design, we have a lot of unique ideas of how you'd run a power plant in order to help reduce those costs. So I don't think I answered your question exactly, but hopefully that gave you a little bit more information. Anybody else? I will make one more statement to that question. We are working very hard to make our design cheap enough to build and maintain that it would be cost competitive with natural gas, natural gas is really the dominant fuel source out there right now. It is by far the cheapest, way cheaper than coal, way cheaper than anything else. There's just so much gas available in the United States. The price has just plummeted, and it's incredibly cheap to burn natural gas right now.
Did you still have a question?
All right,
Yeah,
so the code.
I have a question just about you mentioned that there will be dry cooling for the site at the INL. Is that more expensive to produce than the cooling towers, and has that technology been used in the past?
It's been used in the past, but not in the nuclear industry. Dry cooling is a proven technology. We're exploring it for nuclear. It's a new application for nuclear. There's some advantages and some disadvantages. What you're going to likely wind up doing is trading plant electrical output because it is less efficient. But the costs on the INL reservation for water are so high that it likely could wind up being a wash. We're kind of working out that idea of how's the design going to work and what are the finances going to look like long term. We're just not looking at a cost to build the plant. We're looking at a cost to operate it over its entire expected life when we compare those costs. So I can't really answer your question right now. There's some trade-offs that are going to happen, and it may wind up being cheaper. It may wind up being more expensive. On the surface, it appears like it would be more expensive, but we think there's probably some savings in there, equipment maintenance and some other stuff. A forced draft cooling tower has motors and fans that have to be maintained, and the cooling towers don't last forever typically either. They have to be replaced or repaired often. So there's lots of costs out there that we're trying to discover and make sure we understand before we move forward with that.
One more question. Actually, I've got several, but when you, I don't know the process of getting approved for this with the NRC, but what was the most difficult thing for them to approve for this whole design?
That is an excellent question. I'll tell you a story. I came in 2014. I got to do a couple of site tours at the offices. I was very convinced by the design. I especially being a former engineer, engineers have this terrible habit of liking things more complex to solve problems. I love the concept that it was a simple design. Now, saying that, there was some very unique things, some very challenging things that Nucl was presenting the NRC to approve. So two of the biggest, and I'll give you this, was number one, our staffing plan for the licensed operators. I was told under no uncertain terms that there was no way in the world the NRC would ever approve our staffing plan. And I'm going to tell you a story in just a minute about exactly how that staffing plan currently works. And the other piece was the lack of safety-related DC power. So we don't require AC, safety-related, the plants I was licensed at required safety-related AC and DC power. So we needed a diesel generator and a connection to the grid to provide AC power to the site that was safety-related, very reliable. It could be proven to be very reliable. And we needed batteries, large banks of batteries that were safety-related and were pedigreed, and we could ensure we're able to meet those DC power needs. The AQ1000 design that Westinghouse put forward got rid of the need for safety-related AC power, but us going to the point where we could get rid of safety-related DC power was really quite a step for the NRC to approve. So to me, those are the two biggest things. No safety-related DC power and the staffing plan were the two hardest things for the NRC to accept from our design. And we are sitting here today with a plant design that's approved by the NRC that accepted our staffing plan, and we don't have any DC power. So two big success stories for NuScale, really.
I mean, how is it different? Would you just have, by staffing, do you mean people that run it? Is that what
Yes.
you mean?
So,
Okay.
okay, I'll skip ahead because most of this stuff's not all that interesting, and I found the slide I wanted to anyway. We may come back to some of this. All right, so reduced operator staffing. So this is the part of the process that I was most heavily involved with during my 6 years there. What is traditionally required for a plant is that you have, right now in the regulations, there's a regulation called 10 CFR 5054M that describes what your licensed operator staffing must be for a plant. And for example, for a single unit in a single control room, you need to have 2 reactor operators and 1 senior reactor operator on staff. Nowhere in that regulation does it recognize a control room where you are operating 12 units from a single control room. And never in the current regulation would they drop below, at a minimum, a single reactor operator for each unit. So from that, you could extrapolate out that a NuScale combined 12-unit control room would require 12 reactor operators and probably 6 senior reactor operators to supervise them. If you tried to fit us into the current regulation, and there's actually nothing in the current regulation that fits that. We proposed to the NRC in the design certification application to operate the plant with 3 reactor operators and 3 senior reactor operators. Quickly, reactor operators fill a role of, they are the personnel that are operating the controls in the control room. So we have 3 of those. The senior reactor operators serve a supervisory position. They oversee the reactor operators and the overall operation of the plant. Looking out here, I can just show you the positions. This is actually a person that's sitting in as the control room supervisor, so they would hold an SRO license. Down below, we've got actually 3 workstations for the 3 reactor operators, and one of them standing up at one of the up panels. So very, very different concept of how that would work. Now, after we got all that done and submitted for the DCA, really all of this is based on a human factors engineering principle called workload assessment. So we're just putting the operators in these seats and running them through scenarios and demonstrating that they can perform the work necessary from the plant. So after we completed all that work and got all that information submitted for the design certification application, the one that's currently approved, we did some additional work. We have actually currently demonstrated that we can reduce the operator staffing even further, and have submitted a publicly available topical report that describes a staff of 2 senior reactor operators and 1 reactor operator for a NuScale control room. So, yes, we're working very hard on reducing that staffing. Any other questions? Now, additionally, for your interest, from a staff standpoint, so we're talking about licensed reactor operators. That's one position. We also currently expect to have 4 non-licensed operators, which would be in-plant operators out in the spaces, turning valves, doing other work. You always have to have a radiation protection technologist on site, and you always have to have a chemistry technician on site. It's typical staffing. Beyond that, we've got staffing for all the maintenance positions. Of course, that's not just, you don't just need those people. You need enough crews to rotate through all the positions 24 hours a day and staff all those positions. So you need maintenance people, typically broken down into 3 disciplines: instrument and control maintenance, mechanical maintenance, and electrical maintenance. And you need some management folks. Really, that's what it winds up coming down to.
You guys have a good simulation, like a simulation, training type in your type of, I don't even know how to ask the question. For your control operators, do you have a simulation training package of some sort? Like that?
Yes. So I think I can answer your question. Yes, we do. When we also had to do for the DCA, we had to do a human factors engineering process called integrated system validation, which is part of what this is describes up here. For that, we actually brought in 3 full crews of operators, and we trained them essentially like you would a licensed operator. So they went through roughly 5 months of training, and then we ran them through a series of scenarios, built different crews out of them, and then ran them through a bunch of scenarios and tested them. So yes, we have built an operator training package. What we did for integrated system validation took them about 5 months. We think a full class to meet the NRC regulation would take in the neighborhood of 9 months right now. And we're working to continue to develop our training material for that class.
Can the university be part of that training?
So not traditionally. Traditionally, licensed operator training and qualification and the licensing process is handled by the utility. They hire the instructors, they run the classes, they do all that work. The class you guys are going through would actually be an intro to that whole thing. This introduction to power plant operations, a 2-year degree. This has been, this program has been built in several community colleges throughout the country. But no, the actual licensed operator licensing has traditionally been done by the utility and not by the university.
This degree gets you the job where they will then train you to operate their reactor.
I have a question.
Yeah. Oh, go ahead.
Well, you talk about, getting these small modular reactors, as small and efficient as possible. What do the next 10, 20 years look like? Do you have other patents or designs in progress that are even smaller? Or are you trying to get something approved by the NRC? Like, what does that look like for the future?
So we're currently exploring other designs. Probably nothing I can really talk about yet. But I can talk about the other examples that are out there. So, for example, the company Oklo has submitted a application recently, I think in June or July, maybe May, sometime this summer. They submitted an application. They intend to build a small, I think 5 megawatt electric, what's termed a microreactor. It's actually, from what I can gather of the design, it's a liquid metal reactor, similar to, would be based off some of the technology that was developed at INL at a couple of the experimental breeder reactors on site. So they're advancing that. It would be a small 5 megawatt, they term microreactor. Very low, very, very low staffing requirements. I've seen a bunch of other news out there about very similar designs that are floating around out there. In terms of the small modular reactor arena, for American companies, we're pretty much the only design available right now. For example, we had a competitor that Babcock and Wilcox was putting forward called Empower, and they wound up folding shop several years ago. So there's a few other ideas out there. GE has what they call the PRISM design, which is also a liquid sodium reactor, I think. So it's cool. It's not light water. It's actually liquid metal. There's also some lead designs out there. Our friend Bill Gates is involved in a company called TerraPower that's building a traveling wave reactor, which is another interesting design I probably don't have enough information about to talk about. So yeah, there's a huge interest in nuclear power right now. To me, a lot of small companies exploring options to build different designs. The other major design that's always been out there that has had a lot of support is a gas-cooled design. They use typically called a pebble bed design. They use essentially balls of fuel that are essentially the size of a billiard ball. They use typically helium as their coolant. And I know there was an effort a long time ago, probably 20 years ago, from a South African company that was trying to build and license them here in the United States. And there's a couple other designs that are exploring that now. I think X Energy has that same design, and they're partnering with a large utility in the south of the United States. That's a bit of a ramble, I'm sorry, but there's a lot of design work going on out there right now, a lot of proposals. And there's always fusion, but to me, fusion's always been 30 years away, but I'll try not to disparage fusion too much. Fusion would be great if we could get it to work. It's just a wildly complex process, and I believe it's always going to be a wildly complex and difficult process. All right. Anybody else got any questions? I got to figure out how to fill up 10 minutes here. I'm trying to find my UAMP slide. Oh, there we go. Okay, so you guys, we talked a little bit about UAMPs, just to give you a little bit of information on it. So UAMPs, the Utah Association of Municipal Power Systems, has members in several different states. I think Wyoming, Utah, Arizona, New Mexico, and possibly Idaho, but I don't remember, and maybe Montana. So they're the ones that are working on our first deployment, a 12-module plant within the Idaho National Lab site. Our site is on the far western edge of the Idaho National Lab site. I don't know how many of you are familiar with the layout of the site. I actually was able to visit this spring and actually drove out to the site for the first time, so that was pretty exciting for me. And yeah, well, you know, that's UAMPS and what they're pursuing. We're waiting to hear back from them. Hopefully the end of this month, we'll hear some good news from them that they're ready to proceed with the next stage of the project. All right. Any other questions I can answer? Anybody want me to? Sorry,
Yes,
I flipped through my slides, but go ahead.
Just a question about the political side of the UAMPS situation. I just read a little bit about it and some of the concerns they have for not funding it. Are you familiar with those, and do you have anything to say that, I mean, I have some specific stuff I can ask you about it. Do you have any to that?
I can comment as best I can. Obviously, I'm a bit limited on what I can tell you. Honestly, though, I don't have a lot of information that you guys don't have already. In order to move on to the next stage of the process, which would be to initiate a combined operating license application, they need to maintain 150 megawatts of subscription. They're currently over that. So UAMPS is a subscription model where these municipalities decide to subscribe to a project by basically giving UAMPS money and funding their project. Currently, they have sold over 150 megawatts of subscription. There were a couple of municipalities that dropped out at this point. But supposedly by the end of the month, if you have not dropped out, then you're in by default. And there's still over 150 megawatts in the subscription. So we do anticipate at the end of the month, UAMPS telling us, hey, we've got our money, we're going to move on to the next stage. Certainly there's a lot of political resistance to nuclear. We as an industry, I would say, have done a very poor job of educating people on the real concerns and hazards behind nuclear power. Because to me, from my experience of working in the industry, obviously I've been indoctrinated and I have a biased position, but I'll still supply it. It's an incredibly safe technology. I mean, you can compare it to any number of different other technologies that we developed as a race, and you know, there's a lot more dangerous things out there than nuclear power. We really shouldn't be focusing the efforts we are on trying to resist nuclear power. Nuclear power could solve the climate change crisis right now if we had really invested in it back in the 60s when we had the chance. So there's my opinion on the whole matter. Certainly there's a lot of people that are scared of it because they don't really understand it the way I view it. Oh,
We probably actually need to let them head to their next class. So
can I do one more thing?
Sure.
Can I do one more thing, Mackenzie? And sorry, this is a little bit of an add-on to what I talked about earlier. So to kind of add on to my opinion here a little bit, sorry. This individual, there's a professor at, I believe, Stanford named Jacobson. I think his name's Mark Jacobson. He put out a study that a lot of the wind and solar advocates are using as the basis for the fact that a grid could be entirely powered from wind and solar. His study has been what do I say? There's significant shortcomings in the study. He put it out in the scientific journal. There was a great deal, a large number of scientists that said his study really wasn't complete, really wasn't correct. So that's just one of those things where I struggle with the idea of, you know, we're using bad science in terms of his study to generate all this support for wind and solar when it's probably not the right way to go. And it's probably going to waste a lot of resources that we shouldn't have wasted when we could be using something that's a proven technology like nuclear to solve the climate crisis. Okay, now I'm done.
All right, well, thank you very much, Doug.
Thanks. Appreciate the time to talk to you all. Hopefully I answered your questions and you're a little more informed about what NuScale is and what we're trying to do moving forward.
All right, have a good rest of your day.
Thank you.